So, definition for a mole, what should I write here? What? If I had instead written define a dozen, what would you write? It's just a number. Why do we need a number this big? Molar mass of dihydrogen pentoxide. So it's like a 14 plus, or times 2 plus 16 times 5-ish. What we got? Anybody remember? So 14.0078. 78? Periodic table. Nitrogen's mass. Periodic table. 67. Dang. Okay. Times 2 plus 15.9994 times 5. So 108.01. And then what are the units? No. Grams. Because I'm asking about a mole of them, so it's going to be a gram number. How do you count stuff out by massing them? Okay, so mass out. Now what?
You mass out like all substances, like not all substances, but like multiple stuff. You mass out like one of them and multiple of them, and then divide.
That's what we're looking for. We're looking for the multiple of them. So I got an object. It's a chunk of iron. So I throw this chunk of iron on the scale and I mass it out. How many irons are there? What do I need to divide by?
One.
The weight of one iron. So what I need is to the total mass of everything, and then divide by mass of one. I don't know, components, particles, whatever you want to say. All right, you've got 5 moles of glucose. How many moles of carbon do you have? 30. We okay with that? So if I told you you had 1 mole of glucose, that means you've got 6.02 times 10 to the 23rd glucose molecules. But inside every single glucose, how many carbons are there? 6. So I have to take that 6.02 times 10 to the 23rd number and multiply it by 6. But forget about the 6.02 number. Let's just use the word mole, okay? So I have 1 mole of these. How many moles of carbon are there? 6. How many moles of hydrogen and oxygen? But I have 5 moles. So I just multiply the number of moles times the number of particles in that object. 30, and then 60, and then 30.
So unless they're asking about the number of in the mole, you just have to work with like.
Just work with the mole. It's sort of like asking, somebody gives you 36 donuts and they want to know how many donuts are there. What could you say? 3 dozen. So instead of using the actual number, you could just use a unit of that amount. Makes it easier for, I mean, it's not really hard with a number like 36, but if you went and bought, I don't know, 30 dozen donuts, that you'd probably rather say it as dozen, right? Because then you can think about 30 boxes of donuts I gotta like fit in my trunk or something like that. If somebody said, you go get 600 donuts, you're like, what's that look like? Can I fit that in my car? And if somebody says it's 30 dozen, you're like, oh, yeah, I could probably fit 30 dozens of donuts in my trunk kind of thing. Okay, so the answer is 30 mole of carbon, 60 mole of hydrogen, and 30 mole of oxygen. Clear? See through this. Sure. How about no color? And definitely not the same thing, right? If you're colorless, you are also what? You're also clear, right? But if you're clear, you're not necessarily colorless. Describe what happens in an ionic compound when a soluble ionic compound enters water. So what happens to table salt when that salt crystal hits the water? Okay, it dissolves. What else we got? I like that. Ripped apart by H2O molecules, leaving ions surrounded by water molecules. So when that ionic solid goes in, if it's soluble, what I want you to think about is they're all joined up in a nice matrix, like somebody took a bunch of Legos and put them all together in a nice box. There's no gaps between them or anything. And then the water comes in and disassembles every single one of those Legos away. And now they're completely not touching each other. And they're in a new state, and we call that aqueous. All right, so I want three ionic substances that are soluble and not soluble. You can only use the same ion once. Or you can only use an ion once. So give me something soluble. NaCl. Great. Can't use Na anymore because it's already been used. Oh, no, that's not a compound. I can put, let's put NO3 here. What do you want to put on the other side? So, K? That's great. That's definitely soluble. What else we got? Another compound. Li and literally anything, right? Anything you want to put up there, because these three here are all group 1 metals, and so they're in the first rule, meaning when they hit water, they're soluble. It does not matter that the anion might not want to let go. It's already gone. It's a compound, so you have to have an anion and a cation. So you need both of those components there. All right, how about something that's insoluble? Iron 3 oxide? Okay, Fe2O3. Great, totally not soluble. What else we got? Give me an anion or cation that's not soluble. AgOH. Absolutely. If the water was super basic, meaning it had a whole bunch of OHs in it, if you threw silver ions in there, the water's pH will return to 7. What else we got? What? I need more. I'm good with lead, but lead what? I need a compound. Sulfate? Okay. That is an insoluble substance. So even though the last rule on the list said sulfates were soluble, like 4 rules above that, it said leads were insoluble. So it supersedes that. So that sulfate is definitely insoluble. Okay. So what should I put on the other side here? Based off of what we did in class yesterday with those reactions in water, what belongs on this side over here? Okay, AgBr, and what should I put down for its state?
Solid.
It's a solid because bromides want to be soluble, but silvers want to be insoluble, and the silver rule is one above the bromide rule. And then what do I have left over? I've got a magnesium and I've got a nitrate. I'm going to need a 2 here. Why do I need to put a 2 down there on that nitrate? Yeah, because we're talking, you should be able to look at this and see that this magnesium here is a +2, -1, +1, -1. We haven't talked about balancing yet, so we won't really worry about that, but you would need to balance this. All right, so names. What's the name of the first substance? Magnesium bromide. Next one. Silver nitrate. Next one. Actually, somebody already said it. Silver bromide. And the last one is nitrate. Okay. So that first equation is sort of misleading, right? It's not sort of misleading. It is absolutely misleading. It makes you think that the magnesium and the bromine are floating around in the water together in an aqueous state, and that's not possible. So what does that AQ mean? They're already been broken apart and dissolved, and they're completely surrounded by water molecules because that substance was soluble. So the water came into the MgBr2, broke them apart, and each of the Brs and the Mg are surrounded by water molecules, not touching each other anymore. But we write that first one because it's quick. What we should be writing is magnesium with a +2 charge, that's aqueous, plus 2 bromines with a -1 charge, that's aqueous. So somebody tell me why I did that. Why is the 2 all of a sudden out front? There's 2 Br negatives. Up top, the 2 is a subscript because that's a whole molecule and everything's connected together. The 2 is out in front of the Br now because what did we just say happened to all those ions? They're surrounded by water molecules. Nobody's touching anybody else. So there's literally 2 different bromines surrounded by different sets of water molecules nowhere near each other, flying chaotically through the water. All right, so I still have a substance that's aqueous. So I've got this silver that's aqueous. And then I've got this nitrate that's aqueous. And then I go over to the other side over here. What do I do with my silver bromide? Tell me why these over here got broken apart. Why are the magnesium, bromine, silver, and nitrates disassembled in the full ionic equation? Because they are. They are disassembled. How do I know that they're disassembled? Because it says AQ up there. So now I'm on the other side of the equation. Something's happened. So now what do I do with the silver bromide? It is together. It hasn't separated. I was told that it's a solid. So on this side, I say silver bromide. That's a solid. I leave them together because they are together in this test tube or beaker or whatever. But what about the magnesium and the nitrate? I'm a jerk for not writing AQ here. So we knew that. But you're right. The magnesium is aqueous by itself. And then the nitrate, 2 of these nitrates are aqueous. There we go. Okay, so who is a spectator ion? Not the silver. How do you know? Why is the nitrate? You're right.
Because it's floating around. It's dissolved.
On this side over here, it's a nitrate floating around by itself as an aqueous. And on this side over here, it's a nitrate floating around aqueous by itself. So a chemical reaction happened, and it just sat there floating around in the water, and it never did anything. Anything else? Who else is the spectator ion? The magnesium is sitting here floating around in water, and here it is still floating around in the water. So those things that I have circled, They didn't do anything. They're chemically exactly the same on both sides. Remember what our definition, and it was on the exam, what's the difference between a chemical change and a physical change? The formula has to change, right? Did this formula change for the magnesium or for the nitrate? Everything's the same about it, so no chemistry happened to it. It was a physical change that they dissolved. But the silver and the bromide, what happened to them? They turned into something new. That's a new compound. I have a silver by itself over here, and over here it's physically stuck to a bromine. This bromine's by itself. It's not by itself over here. So the actual chemical reaction that happened was a silver that was aqueous ran into a bromine that was aqueous and turned into silver bromide. Okay.